Okay, good morning students. So we are starting the portion on lateral load analysis of multi-storeyed building frames. So multi-storey building frames, they are highly indeterminate, and so the usual methods of analysis which you have studied, slope deflection or moment distribution or Canny's method, they will become highly computationally involved. Lot of calculations works will be required as the indeterminacy increases. Hence we go for approximate method of analysis. And for the horizontal loads, that is wind load, earthquake load, the analysis, we have three different methods: portal method, cantilever method and fractional method. Of that we are going to discuss the portal method today. So the portal method, let us consider with an example. I am considering a multi-story building frame, 1, 2, 3 bays and 2 stories. The height of the story is 3.5 meter. The first story and the bottom story. The beam spans are 7 meter, 3.5 meter and 5 meter, which is subject to two horizontal loads, 120 kilonewton at the top level and at the first floor level 180 kilonewton. Okay, now we will start the analysis. This method is based on certain assumptions. The first assumption is there is point of contraflexure at the midpoint of all the elements. Point of contraflexure. Point of contraflexure means zero bending moment. At that point, the bending moment will be zero. It is marked here in all the beams as well as in the columns. I have marked it. The second assumption is the horizontal shear force in the inner column. So these two are inner columns. These are the outer columns. The horizontal shear in the outer column, say if it is P, that in the inner column will be 2P. Similarly, in the first floor or the bottom story, I will mark it as R, 2R, 2R, R. So the second assumption is horizontal shear in the inner columns is twice the value of that in the outer columns. These are the two assumptions. Another one thing is, third one, uniform stiffness for all the members. Uniform stiffness means the moment of inertia same for all elements, that is columns and beams. Moment of inertia is same for columns and beams. Then fourth assumption is the loads are acting, the lateral loads are acting only at the joints. So these are the four assumptions of the portal method of analysis. Now I will pass on to the various steps in the analysis. So the first step is step 1, horizontal shear in columns. The horizontal shear in columns, see, P, 2P, 2P, P. So we will consider the top story. This is the top story. This is called bottom story. Consider the top story columns. Consider a section passing through this point of contraflexure and consider the forces above that line. Like sigma H is equal to 0. So we will get P plus 2P plus 2P plus P is equal to 120. Consider a section passing through this point of contraflexure, the columns, and consider a section above that. Sigma H is equal to 0. We will get P is equal to, this is 6P is equal to 120. So P is equal to 20 kilonewton. Now coming to this bottom story, consider a section passing through this bottom story. Consider the horizontal forces above that line, sigma h is equal to 0. We'll get R plus 2R plus 2R plus R is equal to 180. So we'll get R is equal to 6R is equal to 180. So it is 180 plus total load, 180 plus 120, the total load above that line. So this will be 50 kilonewton. So the first step, we have got all the horizontal shear. So this force is 20, this is 40, this is 40, this is 20, this is 50 kilonewton, 100 kilonewton, 100 kilonewton, 50 kilonewton. That is the first step. Now coming to the second step, step 2 is moment in columns. Column, the top story column is AE, BF, CG, DH. These are the top story columns. We'll consider the first top story columns. Moment in this column AE. Moment in column AE. If you consider this end A, this load is horizontal force is 20 kilonewton, 20 into this distance. The distance is height of story by 2. So the moment at column AE, at the end A is 20 into 3.5 by 2. So it is 35 kilonewton meter. See, there is point of contrafluxure here. Point of contrafluxure means a point where the bending moment is 0. So if there is point of contrafluxure, the moment at one end is, say, if it is M, the moment at the other end will also be equal to M. So that when, if it is at the midpoint, by symmetry, both these moments should be of equal value. If this is clockwise, this has to be, that's also clockwise. Both these moments are of the same nature, that is clockwise moment. If it is at a point of contrafluxure at the midpoint, what does it mean? If it is a clockwise means, we have the sign convention for a clockwise moment left of section, it produces sagging. A clockwise moment, this is a sagging moment, isn't it? So if there is clockwise moment on the left, that is a sagging moment. Left of section, if the moment is anti-clockwise, we call it as hogging. These concepts you have studied in the third semester. So point of contrafluxure, since we are assuming there is point of contrafluxure, the moment at this end as well as this end will be having the same value, numerically same value. So according to this, both of them are same, and clockwise means if this portion is sagging, this portion will be subjected to hogging. So in the column, due to this lateral force, the moment at the two ends will be, if one is sagging, the other end it will be hogging moment. Okay, now I mark it in the figure. I'll repeat it once again. The moment in the column AE is 20 into 3.5 by 2, 35 kilonewton meter. This is, thumb goes in the clockwise direction, so the moment here will be anti-clockwise. This is anti-clockwise 35. So this should also be anti-clockwise 35. So moment MAE will be the same as moment MEA will be 35. Both of them anti-clockwise. Considering the outer column DH in the top story, DH, moment in column DH will be the same as moment in the column at the end HD. Both of them will also be equal to that 20 into 3.5 by 2, 35 kilonewton meter. So moment in the outer column 35, here also it is 35, here also it is anti-clockwise 35. Coming to inner columns, moment in BF will be the same as moment in FB. Here also same force. So moment in CG will be same as GC, and each of these will be equal to 40 into 3.5 by 2 will be 70 kilonewton meter. So similarly, this moment here is 70. The moment here is 70, anti-clockwise moment 70. So now we have got the column moments in all the columns in the top story. Coming to bottom story columns, column EI, moment in column EI is the same as moment in IE. Similarly here in the outer column, moment in HL, MLH. All these are same. It is 50 into height of that column is also 3.5. So height of the column by 2. So it will be 87.5 kilonewton meter. Coming to this inner columns, MFJ, MJF, MGK, MKG is equal to the load. Horizontal shear 100 into H by 2. It works out to 175 kilonewton meter. So the column moments here are anti-clockwise moment 87.5. Here also anti-clockwise 87.5. Here 175. Here same 175. Here these two 175. These two 87.5. So thus we have got the second step completed. We have got the moments in all the columns. Now the third step is step 3. Beam moments. For the beam moments, we have to consider these are the beams AB, BC, CD. We will consider the top beams or the roof beams. Consider these beams. Consider this joint A. Consider joint A. Considering joint A, in this column now we have got the bending moment is 35 kilonewton meter. So if you consider beam BA, the moment at this column in the beam AB at this end should be, in order to have equilibrium, this if it is anti-clockwise, the moment here should be equal to clockwise, and that is equal to 35. Now since there is point of contraflexion, the moment at B, that should also be equal to 35 clockwise. So MAB equal to 35 kilonewton meter clockwise. Moment in the beam. Moment in the beam at the end B, MBA, that is also equal to 35 kilonewton meter clockwise. Now, coming to the second column, here the column moment is 70 anti-clockwise. So, the moment in the column is 70, it's already got value. The moment at this joint for the beam is 35. So, what will be the bending moment in this portion BC? If you consider this beam BC, what will be the moment at this point MBC? For that, you consider the equilibrium of this joint B. Consider joint B. We have MBA plus MBF plus MBC should be equal to 0, isn't it? Considering the equilibrium of joint B, MBA, MBC, MBF should be equal to 0. Of that, MBA is 35 clockwise. MBF is anti-clockwise, so minus 70 plus MBC is equal to 0. Therefore, MBC is equal to, we will get it as 35. Or by looking into the figure itself, there is anti-clockwise 70, there should be clockwise 35. Here also there should be clockwise moment 35. So this joint is in equilibrium. That is one way you can do it. Otherwise, just remember, if this column moment is 70 kilonewton meter, since the moment of inertia of all the columns are same or the stiffness is same, that will be equally shared by these two beams. The moment in this column will be shared equally by the two beams MBA and MBC. So 70 by 2, 35 each. That is the easy way to remember. Since the stiffness of the columns is one assumption, stiffness of all the columns and beams are same. So now we have got the bending moment in up to B. Now coming to joint C. Come to joint C. Joint C. That column downwards is CG. That column moment is 70. Since you have got MBA as this moment we got 35, this also we got 35. So definitely this moment has to be 35 and this should also be 35. The moment 70 is shared by these two beams. MCB is equal to MCD and both will be 35 kilonewton meter. Coming to joint D. Joint D, the column moment is anti-clockwise 35. There is point of contrafluxure here. We have got MCD as 35, so this should also be 35 from the first beam itself, or in order to have equilibrium, if this is anti-clockwise 35, this MDC should be equal to clockwise 35. Thus we have got the beam moment in all the beams in the top story. This is 35, this is 35, this is 35, this is 35, 35, 35. All the beam moments are same value, 35 kilonewton meter in the top story or the roof beams. Similarly, we can apply the equilibrium equations for the next level. Coming to this top beam of the first floor, consider point E. In point E, the column moment in EA, here it is anti-clockwise 35, here it is anti-clockwise 87.5, point of contrafluxure is here, and EF this moves to F. So what will be the bending moment in EF? Considering this being bending moment in EF, if you want to get it, we have already looking into the figure. This is anti-clockwise 35, that is anti-clockwise 87.5. So these two together will contribute to 122.5 anti-clockwise. So for equilibrium there should be a clockwise moment of 122.5. We can do it very fast without calculations. Otherwise, coming to the principle, sigma m is equal to 0. MEA plus MEI plus MEF is equal to 0. So MEA is minus 35, MEI is minus 87.5 plus MEF is equal to 0. Therefore, MEF is equal to 122.5. That means clockwise. We got the bending moment in the beam at this end as clockwise 122.5. Now coming to this joint F, if this is 122.5, this should also be equal to 122.5 because there is point of reflection. So now coming to joint F, come to joint F. From if this is 122.5, this should be 122.5. In the top column, FB. This is my market F. FB, there is anti-clockwise moment 70. Here, the anti-clockwise moment 175. So what about this? You want M, FG. FG, see here the value is 122.5 clockwise. 175 plus 70, total unbalanced moment in the column 175 plus 70, 245 minus this 122.5, this will work out to clockwise moment 122.5. Write the equation if you want. 122.5 this moment minus 175 minus 70 minus MFG is equal to 0. Therefore, MFG is equal to 122.5. That is one way. Otherwise, the easy way to remember is total column moment 175 plus 70 is 245. That has to be shared equally by the two beams. 245 by 2 is 122.5, 122.5. Thus, we got the bending moment in the beam FG. So, this is also 122.5. Here also it is 122.5. Coming to joint G. At joint G, here you have 122.5. This column moment is 175. In the upper column it is 70. So what is the moment? GH. What is the value in GH? So if you want to find MGH, this is 175 plus 70, 245. Anti-clockwise. This 245 has to be shared equally by the two beams. So 245 by 2, 122.5. So the moment in this GH, this is 122.5. So this should also be equal to 122.5 MHG. So MGH equals 122.5. That should be equal to MHG. Now we can check this card is correct. Come to joint H. You come to joint H. In the joint H, in this beam, it is 122.5. That top column is 35. The bottom column 85. You check whether sigma m is equal to 0. 87.5 plus 35 is 122.5 anti-clockwise. This clockwise 122.5. So it is okay. So now we have come to the third step. We have got all the beam moments also. Okay. Now in the previous steps we have arrived at the beam moments. So I have marked it in the figure. So beam moment in all the roof beams, it is 35 kilonewton meter clockwise. And beam moment in the first floor level, it is 122.5 kilonewton meter. clockwise. Next is we have to find out the shear force in the beam. This is point of contact flexure. I marked this shear force. If on this side, if it is upward, on the other side it will be downward. And how will you find out the shear force if you have the bending moment? So consider a beam. Suppose it is having a moment m here, clockwise. Here also it is having a clockwise moment m. What will be these reactions? How will you find out these reactions? Each of these reactions will be m plus some. Total unbalanced moment, it is 2m divided by the span. So the shear force will be equal to 2m by n. Okay, if the bending beam is subjected to moment of same magnitude at both ends, the shear force value will be equal to 2m by n. This you know already from your previous knowledge of bending moment. So I write here shear force in beam AB. Consider beam AB. This shear force will be equal to shear force at A will be equal to 2 times the bending moment, 35 plus 35, 70 divided by the span. So it will be 10 kilonewton. So I can mark, if it is left up, right, it will be down, 10 kilonewton. So at the end A, if it is upward, at the end B, it will be downwards. Coming to this beam BC, shear force at B will be 2 times 35 divided by the span. Span of that beam is 3.5, so it is 20 kilonewton. So this value is 20. If at B, if it is up, at C it will be down. Now here, coming to beam CD, shear force at C will be 2 times 35 divided by the span 5. So it is 14 kilonewton. So if this is 14 upwards in this side, it will be 14 downwards on the other side. Similarly, coming to this bottom beams or the top beams of the first story, this bending moment here is, consider beam EF. Considering beam EF, the total moment is 122.5 plus 122.5. The shear force at E, on this side it will be 2 times 122.5 divided by 7, it is 35. This will be 2 times 122.5 divided by 3.5, this will be 70. 2 into 122.5 divided by 5, this is 49. So now we have got the beam shear forces. Beam shear forces are sum of the bending moment at the two ends divided by the span. Okay. Now coming to the fifth step, axial forces in columns. We know how the load transfer action acts in a structure. The load from the slab will be transferred to the beams. The beam will transfer the load to the columns. So the reactions of the beams will be directly transferred to columns. So we will get the axial force. The columns are subjected to axial force. So axial force in column AE. If you come here, consider this joint A. In the beam, the reaction is, or the shear force in the beam is 10 kilonewton. So if you consider this point, the reaction or the axial force in the column should be opposite to that. In order to have vertical equilibrium, the force in this column should be equal to, or axial force in column AE should be equal to 10 kilonewton downwards. This should be not at high vertical equilibrium. If you consider sigma V is equal to 0, there is 10 kilonewton acting upward shear force. So the axial force in this column will be 10 kilonewton downwards. So here it is 10 kilonewton downwards. So at this end, since there is point of counterreflection, means this will be equal and opposite. This point, this shear force here should be equal to axial force in this column in this end will be opposite to that. It will be equal to 10. Now coming to joint B, come to joint B. If you come to joint B, there is 10 kilonewton acting downwards here, 20 kilonewton acting upwards here. What should be the axial force in this column? You can write there. Coming to joint B, column BF. On this left side, the shear force in this beam is 10 downwards. Shear force in this beam on the right side is 20 kilonewton upwards. So what should be the axial force in column BF? What is the unbalance here? 20 upwards, 10 downwards. So the unbalance is 10 kilonewton upwards. So this column force should be 10 kilonewton downwards. So that there is sigma V equals 0. Otherwise, if you don't know to automatically calculate it, you can write down at the joint B, consider joint B, minus 10 plus 20 plus force in column BF is equal to 0. Therefore, BF is equal to minus 10. That means downward. Okay, we can, without drawing the figure and writing the equation itself, we can write sigma V 0. If you apply this, there is 10 downwards, 20 upwards. So to balance this, there should be 10 downwards. Now coming to joint G. See whether we can do it easily. Coming to joint G. Joint C. We are calculating the axial forces here. So here we have got 10 downwards, 20 upwards. So it should be 10 downwards, and here it is equal and opposite, 10 upwards. Coming to joint C, 20 downwards, 14 upwards. So what is the algebraic sum? 20 is acting downwards, so minus 20. 14 is acting upward, so it is algebraic sum is minus 6. Or 6 kilonewton is the net downward force acting here. So the column force should be upwards to have equilibrium. If it is upward in this joint, it will be downwards. Or I'll write it once again. Joint C. On the left of it, 20 downwards. On the right of it, 14 upwards. So the net unbalanced force is 6 kilonewton acting downwards. So for equilibrium, there should be a force acting upwards. So that is 14 plus 6, 20 minus 20, it will become 0. So the column force here is acting towards the joint or thrust. So these two columns are subjected to tension and this is subjected to axial compression. It pushes the joint. Coming to joint D. Joint D, 14 kilonewton is acting downward. So the column force should be equal to 14 kilonewton upward. So this column force is 14 kilonewton upwards. So here it should be in this point, it will be 14 kilonewton downwards. So thus we got the axial forces in all the columns in the top story. Now coming to this bottom story columns. Bottom story columns. Consider joint E. considering joint E, there is an upward force in this top column 10 kilonewton, and in this beam there is an upward force 35. So the net upward force is 35 plus 10, 45. So if it is 45, the axial force in this column should be 45. So from here it is upwards 45. Or sigma b equal to 0. 10 plus 35 plus FEI is equal to 0. From that we can get it. Now coming to this next joint. F. Come to this joint F. There is an upward in this column. There is 10. In this beam it is 35. Right side beam 70. So can you tell me what will be this force in this column FJ? There is 35 downwards, 70 plus 10 upwards. So 70 plus 10 minus 35. 80 minus 35. That will also work to 45 kilonewton downwards. So it will be 45 at this end upwards. Now coming to next joint G. Come to joint G. At the joint G, there is 70 downwards here. In this side, 49 upwards. In the column, 6 downwards. So what will be the force in GK? Total downward forces 70 plus 6, 76. Upward is 49. 76 minus 49, it is 27 is the net force acting downward. So this column force should be 27 upwards. If this is upward, opposite should be downward. So this column is also subjected to axial thrust. Now coming to joint H. If you come to joint H, in the joint H, the column force is 14 acting downward. This side 49 is acting downward. So the net force is 49 plus 14, 63 is acting downwards. So this column force should be equal to 63 kilonewton upwards. So this is 63 downward. So simply by considering the sigma v is equal to 0 at each joint, we can get the axial forces in columns. So we have got the axial force in the bottom column as this column, it is 45, 45, it is 27, 60. Okay, so we have completely done the analysis. We will now check how to draw the bending moment diagram for the beams as well as columns. Here it is shown the bending moment diagram for the columns. I will explain from the beginning. See, at the column for the top story, we have got the value 35 kilonewton meter anti-clockwise at both ends. So it is anti-clockwise. So to draw a thumb rule, I will tell you. Anti-clockwise. So M-A-E. A to E, you face your thumb like this. Anti-clockwise. Move your thumb in the anti-clockwise direction. So mark it 35 here. In the bottom corner here, it is also 35 kilonewton meter anti-clockwise. So E to A, you place your thumb anti-clockwise. The thumb moves in outward direction. So mark 35 here. Join them. Okay, at the center it is 0 moment, point of contraflexion. So this is how we draw the column moment diagram. Bottom column, the bending moment was 87.5 at both ends, anti-clockwise. So with your thumb in this direction, anti-clockwise, 87.5. The thumb in this direction, 87.5 anti-clockwise. So this is the bending moment diagram for the bottom column EI. Similarly, you have drawn the bending moment diagram for all the columns. Okay, and this is marked sagging. Now coming to the beam bending moment. For this beam, we have got the value 35 kilonewton meter clockwise. So you place A to B 35 clockwise. So that thumb comes downward to 35 here. Here also clockwise moment 35. So B to A, place the thumb like this. Move it upward. Clockwise direction. So 35 this direction. So this side it tends to bend the beam up. Hogging moment. Here it tends to bend the beam downward. So it is sagging moment. Similarly for all the beams 35. For this lower level beams it is 122.5 clockwise. In this direction rotate clockwise, your thumb clockwise, so it is downward. Place in this direction clockwise 122.5. Okay, so from these two bending moment diagrams we can easily identify at this junction, say 35 plus 87.5, the column moment totally it is 122.5. So the beam moment should be 122.5, so that it gets sigma m is equal to 0. So this is how we draw the bending moment diagrams for beams as well as columns based on the obtained result. Let me show you the axial force diagram, how to draw the axial force diagram. So to draw the axial force diagram for the columns. Axial force in this column was 10. In this column it was 10. Here it was 6. And here it was 14 kilonewton. Okay. And here it was, the axial force in this was 45. Here it was 45. In this column it was 27. Here it was 63. So these are the values of the axial forces in the columns which you have got earlier. See, the center of gravity of this column falls somewhere here, the vertical axis. This direction is the direction of wind. So the columns on this windward side, we have got tensile force, 10 kilonewton and 45 kilonewton in this column. And the columns on the leeward side, that is on the other side of the center of gravity, they are subjected to compression, 6 kilonewton, 27 kilonewton, 14 kilonewton and 63 kilonewton. Now how to draw the axial force diagram? So here, this is subjected to 10. So we'll 10 kilonewton tension. So I will draw on the left side. To some scale, I will mark 10. Up to this, there is no force. We'll mark it 10 kilonewton, this entire column. Then suddenly, this column is subjected to 45. So from here, you mark 45. So here to here, it is 45. Then here, completely 45. So this is the axial force diagram for this column. It is tension. Similarly, this column 10 kilonewton. Then it is subjected to 45. That is here to here it is 45. So this is also tension. This is compression. This is 6 kilonewton. So compression I will draw on the other side. 6 kilonewton. 27 here to here, 27. Compression. This is 14 compression. So 14, 63 compression. So this is the axial force in column. That is another one important result which I have got from the last step. Now we can show the shear in beams and columns either in tabular form or we can show it as a pictorial representation. I will show here. We have the beams A, B, C, D, E, F, G, H, I, J, K, L. There is point of contrast structure at the midpoint of each beam and at the midpoint of each column. Okay. Now you mark the axial force, the horizontal shear in the column. This column it is 20. The horizontal shear in this column 40. Here also it is 40. 20. Similarly, the horizontal shear in the bottom columns 50, 100, 100, 50 kilonewton. So these are the horizontal shear in columns. Now coming to the shear force in beams. In the top beams, the shear force it was 10. In this beam, it was 20. And this beam CD, it was 14. The bottom beams here, it was 35. This was 70. This beam 49 kilonewton. So it is very important that you have to write the unit in the diagram at least at one place. So here kilonewton, kilonewton, kilonewton. So this shows the shear in beams and columns. So say lengthy example. So the total analysis of lateral load, it involves first step is finding the horizontal shear in columns, then finding the bending moment in this columns, then bending moment in beams, shear in beams. From that we got axial forces in columns. And one check is there. When you get after this, you can check the final axial force in columns considering the base of the columns. The axial force 45, it is 45 tension. This is minus 27. This is minus 63. If you take the sum of the axial forces, it should be equal to 0. That is also a final check. Okay, thank you all.